Welcome back, friends. So in this section we will calculate we know how to calculate the full load current of the transformer at the HV side and LV side. So we can call as full load current as in the short form as FLA. So we have to calculate the full load current of HV side and LV side. So we know that the formula for the transformer power is S is equal to under root 3 V into I. So this formula is applicable for a three-phase transformer. So we are discussing a case of three-phase transformers. So for single phase, just for information's sake, it will be equal to V into I only. So we are not using this here anymore because we are working on a three-phase transformer. So you have to put the values here. So in this case, I is equal to S divided by under root 3 divided by the V. So it means that the voltage, you have to divide the S with the voltage. So if you want to calculate the full load ampere for the HV side, you have to give the HV voltage here. And if you want to calculate the full load ampere for the low voltage side, you just have to give or put the low voltage here. So I will calculate first I FLA HV. So it will be equal to under root 3. It will be equal to 100 divided by under root 3 into 132. Okay, K. So I will write 10 power 3 and here 10 power 6. So if you divide all this, you will get this value here that I already mentioned here, which is basically 473.4 amperes. So it is equal to 437.4 amps. So this is the maximum current, maximum capacity of the transformer. So that's why we are calling it as FLA. So this is for HV side. So in the same way, we have to calculate the full load amperes at the HV side as well. So we calculate full load ampere at LV side, IFLA LV, and that's equal to again 100 into 10 power 6 because it's an MVA under root 3. MV side is 33 kV, so into 10 raised to power 3. So I full load ampere LV is equal to, you can see it's already calculated here, and that's equal to 1749.5 amps. So hence we have calculated the full load ampere for the HV side and also the full load ampere for the LV side. So we will use these in our differential protection setting and calculations. So thank you very much. Welcome, friends. In this section we will study the voltage variations because of the tape changers. So we know that at this transformer the active voltage is 132 kV, the LV voltage is 33 kV, and the tape changer installed here can regulate plus minus 10%. So this is here you can see this mentioned over here. So this is in fact an all load tape changer. So on load tape changer is a tape changer where you can change the taps when still the transformer is on load. So here you can see this is if you want to calculate, so you can calculate using this formula for plus 10%. So you have to multiply 1.110% into 132 kV. So that is equal to 145.2 kVs. So this is the max voltage. So now we will calculate the bandwidth. So this is the max voltage possible at the transformer. So 145.2, and then we calculate the minimum voltage at the high voltage side, and that is minus 10% of 100%. It will be 90% or 0.9% into 132. So if you calculate this one, then it will be 113.80 kVs. So it means that because of tape change, we have the variation of the voltage at HV side between 145.2 to 113.8 kVs. So it means that the transformation ratio for the transformer is not still fixed. It's not a constant. Because of the tape position, it's varying. So we need to consider also this variation in our static calculation, because this will obviously create a differential current in the transformer. So if you see a transformer here, so you can see here that this is not a transformer at which we are doing certain calculations. This is another transformer nameplate. So I just want to show that how the transformer nameplate is showing different taps. So this transformer have the tap available. This is 132. Okay, 132 kV plus 11 taps, and each tap here you can see is of 1.367%. So each tap is 1.367% into 11, so it will be regulation of 1.367 into 11. So almost 15% plus and 15% minus in this transformer especially. So they have mentioned the regulation in this way. And the taps here you can see there are 23 taps are shown here. And in the center you can see this is 132 kV. This is the rated voltage of the transformer, and at this tap, if the rated voltage are coming, secondary side voltage will be 12 kV, and the secondary side, or you can see the low voltage side current is 1250.9 amperes. Rated power is 26 amperes. So this is a different transformer we are just discussing just for sake of understanding. And you can see the HV current here is 113.7 amperes. So this tape, which is 12, is also called as a normal tape. Okay, so it means that this is a normal tape, and it means that at this tape, if you give the voltage, normal system voltage of 132 kV, you will get the normal 12 kV as per design for this transformer. But if, for example, the voltage at the HV side are changing, increasing or decreasing, for example, if the voltage at HV side are coming up to, you can see 144.6, it means that you have to choose the tap position number 5 in that case. So you have to take the tap to number 5, then you will be able to get again 12 kV at the low voltage side. So if the voltage are dropped to 117.6, so here you can see, then you have to select the tap again number 8, and then you can get again 12 kV voltage at the LV side. So it means that we are making low voltage in this case as fixed. So we want to regulate the low voltage side. So we don't want any voltage variation. So if there is a voltage variation at HV side, so we have to change the tap accordingly, and we have to maintain the low voltage side terminal voltages. The low voltage side also, the current also remain fixed, and the HV side current here you can see starting from 98.9 to 133.8, it's keep on changing. So that's why in our differential calculations we have kept the low voltage side as a reference fixed, and we have find out the variations at the HV side. So this is a simple example, and here you can see how they are changing the taps. So you can see this is the HV side, and you can see this is the tape changer winding is shown here. Okay, so in fact it is 100 to 11 taps are there, and then 1 to 11, and then the same winding is being added into additive and subtractive polarity. So just like a cell, and the voltage are being added or subtracted. So this is just will give you a brief idea how the transformer is working. This is important because you want to learn about the differential protection setting calculations. Thank you very much. Welcome friends. In this section we will come to see another topic, and that is the fault or short circuit MVA. So we will see what is a short circuit MVA and what is the relationship of short circuit MVA with the percentage impedance of a transformer. So why we want to calculate the short circuit MVA. So first of all, if you see a transformer, so if I draw a transformer, so this is a simple single phase transformer and it is supplying a load here. So in this case, you can see the current is depending upon the load impedance ZL, for example. If the impedance is reducing, the line current or the load current will increase. But what happens if there is a fault on the line? For example, if there is a phase to ground fault on the line, then you can see easily that the load impedance will be completely bypassed in this case. And you can see, for example, if the neutral of the transformer is also grounded, so the current will flow back to the winding and this impedance is completely bypassed. So here you can see this is the loop or the path of the fault current IF. So in this path, the current will be limited by, so you can see the IF will be equal to transformer low voltage side LV voltages divided by impedance of the transformer. Okay, so this is the impedance of the transformer plus the impedance of the line and the earth resistance. Okay, so this is all in case of phase to ground. But what will happen if there is a short circuit on the terminal? There is a worst case of the short circuit. In case of worst condition is when there is a short circuit on a three-phase terminal of the transformer. So of the three-phase, all the three-phase of the terminal of the transformers are short-circuited. So in this case, you can see the current will be flowing through all three phases, and only thing that is limiting the current here is the impedance of the transformer itself. So this impedance, we can call it as a Z percentage impedance. So here you can see this is 12.5 in this transformer. So as a thumb rule, if the voltage, if you will see this, if the voltage of the transformers are increasing, for example, if there is a transformer 132 by 11 kV, the percentage impedance here you can see is 12.5%. So if you have another transformer that is 11 kV by 400 volts, for example, this is a distribution transformer, you will see the percentage impedance is dropping to 5% or 4%. And if you see another transformer like 220 kV by 132, the percentage impedance will be more higher. For example, it will be 18% to 20%. So if the voltages are increasing, the fault levels are also increasing, and we want to control the fault current in that case. So we can control the fault current by increasing the impedance of the coil itself, because this is the limiting factor in case of fault on the terminal of transformer. And we are designing the transformers at the worst possible faulty condition, and that is normally three-phase short circuit. So this is one case, and secondly, while doing the setting calculations, we have to make sure that in case of short circuit, our differential protection should be able to pick and trip in case of a in-zone fault. So here you can see the impedance, percentage impedance is 12.5 volts. So if you want to calculate the fault MVA, so we know that we have already know the formula of S is equal to √3 V into I. So this is the formula for normal calculations for the transformer, that is to calculate the full load current of HV side and LV side. But the same formula is also applicable for short circuit calculation. S short circuit is equal to √3 V into I. So how you have to find out the short circuit MVA of a transformer? So the formula is quite simple. So you have to divide the MVA of a transformer. So this is MVA, 100 MVA, divided by the percentage impedance, which is you have to divide it by 100, so it's 0.125. So then short circuit MVA will be coming as 100 divided by 0.125. So it's equal to coming as 800 MVA. So you can see here, this is 800 MVA. Here is a short circuit MVA of a transformer. MVA short circuit. So what does it mean? So it simply means, let me make another. So it simply means now we have calculated S here is equal to 800 MVA, and this is the short circuit impedance of a transformer. So this is short circuit impedance. So this is 132 kV by 33 kV transformer. So if I want to calculate short circuit level at the low voltage side, I have to use the same formula. This is equal to under root 3 V into I. So then I want to calculate I short circuit current at the low voltage side, then it will be equal to 800 into 10 raised to power 6 divided by under root 3 divided by 33 into 10 raised to power 3, and that's 3, 6, it will be 10 raised to power 3, so it will be coming like 800 multiplied by 1000 divided by 1.732 divided by 33 divided by 1000. So it's coming as 13.996, or we can see it's equal to 14 kilo amperes. So you can see here the short circuit level at the low voltage side is coming as 14 kilo ampere. So it means that if you are supplying 132 kV at the HV side and the LV side is short circuited, then this much of the current will be flowing through the low voltage side. So in the same way, if supplies at the low voltage side and HV side is short circuited, I short circuit HV, this is LV. So HV, just we have to multiply, you have to change here 800 K divided by under root 3 into 132. So it will be equal to 800 divided by 1.732 divided by 132. So it is almost equal to 3.5 kilo amperes. So this is the case when LV side has a source and HV is short circuited. So in this way you have now calculated the fault current in case of HV fault and LV fault, and you have now understood the relationship between the percentage impedance and the fault MVA and fault current. So this is the basic formula to do the calculation. So when we are doing our setting calculations, we obviously will be using this formula to do our calculations. Thank you very much.